Coming up, the latest quantum computer news from McDade, Quantum Network. We are currently in our subscriber building phase. We need your help. Please take a moment to subscribe to the channel, just like Schrödinger's cat, so that we can continue to provide you with the latest news on quantum computing. Thank you. Zurich Instruments is a test and measurement company headquartered in Zurich, Switzerland. They develop and sell measurement instruments worldwide, directly or with carefully selected partners, and provide responsive and effective customer service. Zurich Instruments are a growing, independent, and founder-led company. Zurich Instruments makes cutting-edge instrumentation for scientists and technologists who work in advanced laboratories and are passionate about phenomena often difficult to measure. Their offering includes lock-in amplifiers, arbitrary waveform generators, impedance analyzers, phase-locked loops, digitizers, boxcar averagers, and quantum computing control systems. System integration leads to reduced setup complexity, more efficient workflows, better time allocation, and more reliable measurements. Zurich Instruments delivers market-leading specifications for sensitivity, dynamic range, feature set, speed, and accuracy, as shown by their numerous industry firsts. Zurich Instruments integrate state-of-the-art analog electronics, high-precision digital signal processing, innovative software, and intuitive user interfaces into a line of products guided by lean design principles. Integration does not stop at the instrument level, however. Their products come with responsive and effective customer service, a high level of professionalism and competence, and complete documentation. Zurich Instruments was founded in April 2008 by Dr. Sadek Hafizovic, Dr. Flavio Here, and Beat Hofstetter as a spin-off from the Swiss Federal Institute of Technology, ETH Zurich. At ETH Zurich, they developed a prototype used by a team of biologists to characterize and sort blood cells using single-cell impedance measurements. The instrument had to be capable of simultaneous high-rate demodulation at multiple frequencies. The solution relied on an FPGA-based digital signal processor and sophisticated software, and it replaced a much bulkier and complex setup. That prototype became the foundation for the first line of highly integrated, multifunctional equipment for time and frequency domain analysis developed by Zurich Instruments. Spin-based quantum computing is a leading technology for the realization of scalable quantum computers. Semiconductor quantum dots, QDs, are used to trap individual charges and the associated spins, which are then used as qubits. The Zurich Instruments Quantum Computing Control System, QCCS, provides all the key tools for spin qubit characterization, control, and readout, providing a low-noise and scalable solution that improves setup reliability and simplifies setup control. Single spins are confined in semiconductors' quantum dots. Metallic gates define them and control the relative couplings. A large quantum dot is used as a charge sensor for the smaller ones, which are serving as qubits. Single qubit operations are induced through an oscillating magnetic field coupled to the qubits through microwave strip lines. 2 qubits gates can be realized with fast pulses on those metallic gates which are close to 2 quantum dots. Measurement strategies. Quantum dot characterization. The MFLI lock-in amplifier is used for quantum dot characterization. The integrated low-noise current amplifier is able to amplify the small current flowing through a typical QD, and the multiple oscillators are set to different frequencies to simultaneously acquire DC conductance, low-frequency conductance, and gate transimpedance. The digitizer function can be used to acquire fast current traces to perform single-shot spin readout. Fast multiplexed qubit control. The HDOG multi-channel arbitrary waveform generator generates the fast pulses for the metallic gates, which are used to control the QD energy levels and couplings and to drive the 2 qubit gates. To counteract the effect of cross-coupling, additional pulses are applied to multiple gates. The HDOG is able to modulate the microwave source in order to produce single qubit gates. Different qubits can be addressed with frequency multiplexing. A single sideband modulation scheme, in conjunction with the internal oscillators, suppresses unwanted images and facilitates a clean spectrum. High fidelity readout. The spin readout speed is greatly improved when performed at high frequency with RF reflectometry. The UFLI lock-in amplifier generates the probe RF readout tone and acquires the reflected response of the sensing QD to perform fast and high-fidelity single-shot spin readout. Up to 8 sensing dots can be multiplexed and read simultaneously. The magnitude or the phase of the demodulated signals is a measure of the complex impedance of the charge sensor, from which the qubit state can be measured. Their measurement systems feature in a broad range of demanding applications around the world. Zurich Instruments has a pipeline filled with projects and innovations, and are open to new partnerships, collaborations, customers, and team members. Support the channel with a $50, $25, or $5 donation, or any other amount you choose. Your donations are greatly appreciated and allows McDade Quantum Network to continue to produce great news and content on the major players in quantum computing.